Hey there, Mike from Prep Pros back with another SAT math video. Now this is going to be a 30-minute crash course covering the 9 most important strategies and topics that you need to know if you're looking to get an 800 on the SAT math section. After working with over 1,000 students and carefully examining the content of over 50 SATs, I've selected these 9 topics as the topics that not only most consistently appear on the SAT, but also are consistent sticking points for students ranging all across the spectrum of math scores. So pay close attention, be active as you're working through those practice questions in this video, and by the end, I can promise you're going to feel significantly more comfortable with the SAT math section. Let's jump straight into it with interpreting constants. Now, this is one of the most common question types on the SAT and is really easy once we know what we're looking for. This concept really focuses around infinite solutions, no solution, and one solutions. Once we know what we're looking for, these questions become really easy. So infinite solutions is often the one that students may remember best from math class. But infinite solutions pretty simply means everything on both sides of the equal sign is going to be the same because these lines are going to have the exact same slope and they're going to have the exact same intercept, so they're constantly intersecting each other. But pretty simply, x's are the same and our intercepts are also the same. Now, the next one we'll go over is no solutions. No solutions is going to be represented by the slopes being the same, so our x values have to be the same, but our intercepts must be different. Now, if we like to think of these visually, this is going to be because we're going to have 2 parallel lines. They're going to be impossible to intersect. Now, the last one we're looking for is one solution. If we have one solution, our only requirement is that the slopes are going to be different. This means at some point, these 2 lines are going to intersect each other. It could be something like 5x plus 7 equals 3x plus 5, or you could also have them having the exact same number, the exact same intercept, so you could see 5x plus 7 equals 3x plus 7. Your only requirement for one solution is that the slopes must be different as we're working through those. So let's take a look here at this question, and this is the hardest question from the October 2019 test. The equation 9x plus 5 equals ax plus b, a times x plus b, where a and b are constants, has no solution. So now what we want to look for is, right, this is what we're thinking about. Our slopes must be the same and our intercepts must be different. Which of the following must be true? Well, first thing we're going to do is we're going to distribute through. So we'll get 9x plus 5 equals ax plus ab. And our first thing is, right, the slopes must be the same. Therefore, 9x must equal ax. Therefore, a must equal 9. Our first statement must be true. So now we can resubstitute 9 back in for a in this equation. So we can rewrite this as 9x plus 5 equals 9x plus 9b. And now we get to our second step. Our second step for no solutions is that our numbers or our intercepts must be different. Therefore, what must be true is that 5 cannot equal 9b. Therefore, 5/9 cannot equal b. And that's going to tell us that 3 must also be true. Therefore, 1 and 3 are going to be our correct answers here. Now, this is going to give you a few more practice questions for the interpreting constants, where we're going to be applying exactly what we just did. And as I said, your answer key is going to be at the back end of the video. Now, the next concept that we're going to go over is a really helpful way to cheat through some of the hardest questions on the test. And this is what I call backsolving with points. But really simply, whether we're dealing with a graphing question or we're dealing with a question where we're given points within the question, we always simply want to plug those values in to try to find the right answer. We want to minimize trying to conceptually do these questions if, in a really black and white way, we can use points to find the answer. So we're going to go through 29 here, but as always, pause the video, see if you can figure it out on your own. Cal measured the temperature of a cup of hot chocolate placed in a room with a constant temperature of 70 degrees Fahrenheit. The temperature of the hot chocolate was 185 at 6 p.m. when it started cooling. The temperature was 156 at 6:05 p.m. and 135 at 6:10 p.m. The temperature of the hot chocolate continued to decrease. Of the following functions, which best models the temperature Tm in degrees Fahrenheit of Cal's hot chocolate m minutes after it started cooling? Well, now we can pull out 3 points. Since it's m minutes after it started cooling, at 6 p.m., this is the beginning point, we're going to have the point 0, 185. And then at 6:05 p.m., which is going to be 5 minutes after it started cooling, we're going to have the point 5, comma, 156. And then at 6:10 p.m., we're going to have the point 10, comma, 135. And now all I have to do, because this is a calculator question especially, is simply plug in 0 for m and see if it gives me 185 out. And then I'll go to 5, and then I'll go to 156. Well, the only one that isn't going to work when I plug 0 in for m is C. But once I plug 5 in for m, the only answer choice which is going to give me 156 or a value close to it is going to be D, and that's how I can really easily start to cheat my way through a lot of questions that you may not normally feel comfortable solving conceptually. The reason that D is right conceptually is since it says a constant temperature of 70, D is the only one that displays 70 as a constant. But we're going to go through how we can do this graphically. Now this is a little bit of a tricky question that routinely gives students a lot of trouble. An equation of the graph shown is ax plus by equals 6, where a and b are constants. What is the value of b? Well, we're solving for b, and b is associated with y. So there's a few different ways I could do this. I could pick the point 3, -1, and I could plug it in. I could pick the point 6, 0, but the best point for me to pick is the point 0, not 2, 0, -2. Because if I'm solving for b, I want to be able to get rid of the x, the a portion, which is attached to x. So all I have to do here is a times 0, I'm just going to plug in that point, plus b times -2 equals 6. Well, a times 0 equals 0. Therefore, I will simply get -2b equals 6. Now I can simply divide by -2, and I'm going to get that a is my correct answer there. Way, way easier than solving this via a system of equations by using multiple pairs of points. Now, same thing here, you're going to get some extra practice with this, and we're going to cover a lot of these vertex questions later in the video as well. Now, the next concept that shows up all the time, and we saw 4 of these questions on the most recent SAT, is percent increase and decrease. Now, this is something that really trips a lot of students up, but once we know what we're looking for, it becomes very easy. And there's 2 varieties of these questions that we want to make sure we're comfortable with. Now, the first variety is simply being comfortable with the basics of percent increase or decrease. Now, percent increase or decrease, and we'll add on to this as we get to exponential growth and decay later, can always be expressed by 1 plus or minus the percent expressed as a decimal, or 100 plus or minus the percent expressed as a number. So if we were looking for a 70% increase, I could express this as 1 plus 0.7. 0.7 represents 70%, and that would give me 1.7. If I was looking for a 70% decrease, I would simply do 1 minus 0.7, which would equal 0.3. I could also express this in terms of 100, is I could do 100 plus 70, which would give me 170%, which is the exact same as the 1.7, just expressed in terms of a percent. Or I could do 100 minus 70, which would be expressed as 30%. But the whole part we need to understand is the 1 plus or minus, or the 100 plus or minus. So here, as we look back at this, the expression 0.7x represents the result of decreasing by a positive quantity by x by what percent? Well, we're going to get to 0.7 by simply doing 1 minus 0.3 is going to equal 0.7. Therefore, this is going to show us a 30% decrease. Now, the other variety that really trips up a lot of students are what we can think of is percent reversal questions. We're still going to be using the same 1 plus or minus concept, but we're adding a little bit something extra into it. And this gives us a great example of this. A quantity is decreased by 45% of its value. So the first thing I would do is 1 minus 0.45, and this is going to equal 0.55. That's going to show us a 45% decrease. The resulting value is x. Which expression gives the value of the original quantity in terms of x? Well, let's say our original quantity is going to be represented by the variable y. Well, what we could say then, right, is y times 0.55 is going to equal x. We're saying we're decreasing by 45%, so we'd be multiplying by that 0.55 that we found here. And now, if we're looking for which expression gives the value of the original quantity in terms of x, Now we just need to isolate for y. So all we would have to do here is divide x by 0.55. We'd get that y equals x over 0.55, and that's going to give us B is our correct answer there. We're just stacking on the 1 plus or minus, but now we're looking at this and we are undoing the percent change, and that's why we're going to be dividing by the 0.55. Now, you're going to get 2 more examples of this, and this will give us a great one where we're more so looking at it. It's the 100 plus or minus instead of the 1 plus or minus, and same 1 plus or minus here that we're looking through. Now, the next concept we're going to take a look at is grafting and shifting functions. So really quickly on the screen, I'm going to pop up from my math book all of the shifting rules that you need to know. But from here, we're also going to be able to use a little bit of that back solving with points that we talked about earlier to help us solve these problems out. We just need to stack on the shifting portion here. So as we take a look at this expression, the graph of y equals f of x plus 1 is shown. Which equation defines the function f? Well, if this is f of x plus 1, if we're looking for which one defines the function, we're going to have to shift it down 1 point. So every single thing here we see is going to have to be shifted down 1 point. So now what we're looking for is if I plug 0 in for the equation, I need to get back out 1. And if I plug 1 in for the equation, I need to get back out 3 instead of the original 1, which is going to give 4. So we're using a lot of that back solving with points. We're just adding the shifts onto it. So now we'll just start with that. We'll plug 0 in for each of these. Well, 2 to the 0 equals 1, so this works. 3 to the 0 equals 1, so that also works. C, 2 to the 0 equals 1 plus 1 equals 2, so that does not work. And D, 3 to the 0 plus 2 is the same as 1 plus 2, which equals 3. So those bottom 2 fail on showing us the 0 portion. Now, the top portion here is all we get down to next. The next point we get to use is 1, 3. So if I plug 1 in for x, y has to equal 3, and that's how I can identify that B is my correct answer there. This will give you 2 more sets of these with practice. We're doing the exact same kind of general thing, still applying our shifting rules and plugging in the points. Now, the next concept here is exponential growth and decay. Now, the basics of exponential growth and decay is this is what we're always solving for. This is going to be represented by our initial amount. This is our 1 plus or minus the exact same way we've dealt with the percent increase or decrease, and this is going to be the number of periods that it's raised to. Now, these questions will go from really easy, you'll see one really easy example on the next one, where as long as you're familiar with this basics, we can find it, to stuff that's a bit trickier, like we saw in the October 2022 example here. Now, this one is also going to let us use some of our back solving with points strategy to help us work through something really tricky like this. So we'll talk through the exponential way as well as the other. The population in millions of Suzhou, China can be modeled by the function p of t equals 1.1 times 1.06 to the t, where t represents the number of years after 1990, and 0 is less than t is less than 25. This just means we can't go past the year 2015. Which of the following equations, best models the population in millions of Suzhou, where n represents the number of years after 1995, and 0 is less than n is less than 25. Now, what we're kind of looking at for our exponential growth and decay is if we kind of unpack this formula, like let's say we just did this to the second. So if we did p of t equals 1.1 times 1.066 to the second, this is no different than p of t equals 1.1 times 1.066 times 1.066. This is all that's happening for exponential growth and decay, is whatever power this is raised to, we're just adding another 1.066. So here, if we're looking for the one that is representative of the number of years after 1995, we simply need to be doing 5 of these, and then we would go right back to our original expression of t, and that's going to add on every additional year. And that's why C is our correct answer here. We're doing our same 1.1, we're doing 1.066 5 times to get us all the way out to 1995, And then for every additional year after 1995, we're multiplying by 1.066 again. Now this can feel really, really tricky. So one thing we could do here is we could apply back solving with points. One of the easiest values I could think about is I could say, well, let's say both of these are going to be hitting the year 2000. Now for the first equation, I'm going to have to raise it to the 10th because that's 10 years after 1990. But in our second equations, since it's the number of years after 1995, I would simply be raising it to the 5th. So a really easy way we can apply that strategy we learned earlier is when I plug 5 in for n in each of these answer choices, whichever one would match up perfectly to what I would get when I plug in 1.1 times 1.066 to the 10th in my calculator is going to give me the right answer. But even looking at that, we can simply see if we plugged 5 in here, if we used our exponent rules, we could just re-express this as 1.1 times 1.066 to the 10th power. They're going to give you the exact same thing, but oftentimes by plugging numbers in, the questions start to feel a lot more obvious as you're working through them. So this is going to give you a little bit more practice with exponential growth and decay. And since 24 is something a little bit unrelated to what we have talked about so far, I'm going to work through this one as well. Now, the given equation models the value of an antique dresser t years after its restoration, where 0 is less than t is less than or equal to 5, which of the following equations best models the value of the dresser m months after restoration? Well, I can kind of use a somewhat similar strategy to with back solving with points, but we'll also talk about conceptually how we can spot the right answer. Well, 1 year is the same as 12 months. So if I plug 12 in for each of these answer choices and 1 in my original expression, whichever ones match up are going to give us the right answer. But this is also why conceptually C gives us the right answer, because 12 over 12 equals 1. So that means every 12 months, we're going to get the exact same 5% increase over the previous year that we would get by using this exponential equation up here. Now, the next concept that tons of students feel unfamiliar with but shows up all over the SAT and really easy to learn is standard deviation. Now, for standard deviation, all you really have to know for the SAT is it's a measure of the spread of values in a data set. This also means that your range is directly related to your standard deviation. If you have a bigger range, if you have the numbers from smallest to largest are spread way further out in one data set compared to another, it's almost always going to have a bigger standard deviation. But also, if data sets are more closely clumped together around the middle, it's going to have a greater standard deviation compared to something where data set, the values are spread further apart. So most of the time with standard deviation, you can really just visually look at it. If data sets are closer to the middle, it's going to have a lower standard deviation compared to something where they're spread further apart. And that's why visually I can look at this question really quickly, and I can see that the standard deviation of data set B is going to be greater than the standard deviation of data set A, because so much of data set A is falling between 15 and 25 compared to having more of these values along the outside that we have in data set B. Now, we could go ahead and manually calculate for the means, but what we can also see is we have 2 that are 10 away, above and below, and we have 5 that are 5 away, above and below. Each of those are going to cancel each other out, and they're going to give us a mean of 20. We can see the exact same pattern below. We have 4 that are 10 away. Those are going to cancel each other out. We have 4 that are 5 away. Those are going to cancel each other out. So the means are going to be equal, but the standard deviation of data set A is less than the standard deviation of data set B. Now, this is going to give you another decently difficult one, but April 2018 example here is going to give you one which is a little bit more straightforward with just identifying the range, and you can more easily visually tell which one is going to have a greater standard deviation because the values have a way greater range and you have more values spread apart at the ends. So either of those things is almost always going to help you visually spot them. Now the next thing we're going to go over is vertex formula. And parabolas in general is a thing that shows up on the SAT a lot, and a lot of students are rusty on this or were never quite taught it very well in math class. So I'm going to pop on the screen really quickly all of the different kind of forms of parabolas that you want to be familiar with off of my book here. But we're going to really focus on vertex because this is what a lot of students struggle with. Now for vertex portions here, and I'll rewrite the formula out on screen, it's y equals a times x minus h squared plus k. This a portion, as we go back to some of those transformations we talked about earlier, is going to affect our kind of stretch and compression, but for almost every SAT question, you just have to understand that positive a is going to make it open upwards, negative a is going to make it open downwards. And now h is going to give you the value of the x coordinate of your vertex, and k is going to give you the value of the y coordinate of your vertex. So if we're looking at this example from October 2019, where we're told a scientist tested a group of adults aged 30 to 85, the graph shows the quadratic function s, which models their scores on a language test as a function of their age x in years. Which of the following could define s? Well, the first thing I notice is this is facing downwards. So that a value that comes before must be negative. So I can get rid of c and I can get rid of d quite easily. Now all I have to do is identify where the highest point on the graph is, and that's going to be where x equals 55 and y equals 50. So I know my x value is here, my y value is here. I'm able to get this right pretty easily. We can apply the exact same series of steps here to help us identify the right answer. So I'm going to let you guys work through that one on your own. You're going to hit 2 additional problems. This is a super tricky one. So this is like an 800 level math problem where this is who decides gets the perfect score. But we're going to have to go ahead and involve this exact formula to help us get there. So this one I am going to walk through because otherwise almost everybody's probably going to get tripped up by this. But take a shot at it on your own. Now a quadratic function can be used to model the height in feet of an object above the ground in terms of time in seconds after the object was launched. According to the model, an object was launched into the air from a height of 0 feet and reached its maximum height of 784 feet 7 seconds after it was launched. Based on the model, what was the height in feet of the object 3 seconds after it was launched? Well, what we know here using that vertex formula is we don't know the a value, but we know the maximum height. So seconds is going to be our x portion, height is going to be our y portion. So we can do x minus 7 squared plus 784, and what we also know is according to the model, an object was launched into the air from a height of 0 feet. So this also means the point 0, 0 is going to appear on the graph. So we can solve for a by simply plugging in 0 for y and 0 for x, and then we can solve for a from there. And once we go through and we solve for a, we simply can plug it back into this portion of the equation, and then we can plug 3 in for x to finish the question. So if anybody gets stuck on that, drop a question in the comments for the rest of the steps, but otherwise I think everybody will be comfortable working back through those steps there. Now, second to last thing here is lines. Now for lines, for the most part, students are comfortable with the basics of y equals mx plus b, finding the slope from 2 points, but what the SAT loves is one really particular type of question. And this is going to be where we're going to either have to solve for the slope using 2 points and then solve for the whole equation of the line, or we're going to have to use a line being parallel or perpendicular to another line to then solve for the equation of the entire second line. Now, I know that can sound a little bit confusing, so we're going to break that down with this example here. So we're told the graph of the linear function f, linear functions are the exact same as line, is shown in the xy plane above. The graph of the linear function g, not shown, is perpendicular to the graph of f and passes through the point 1, 3. What is the value of g of 0? So this is asking us to solve for any time you see g of 0 or f of 0. This is asking you for the y-intercept of that other equation. But the first thing we can do is we can go ahead and we can solve for the slope. Now, what you really always want to do is simply do your y2 minus y1 over x2 minus x1. But here what I can see is I'm going to have a slope of -2. So if this original equation has a slope of -2, the perpendicular line, which is g, is going to have the negative reciprocal, which means you flip the sign and you flip the fraction. So what we now know is for our function g of x, we're going to have the slope of positive 1/2. So all we have to do is we have to solve for the b value. And whether we're asked to solve for a point that is not g of 0 or f of 0, we always have to solve for the intercept first. Lines being parallel and perpendicular tells us nothing about their intercepts. It only lets us identify the slope given another one. But all you have to do from here is once you get to this step, which you can always get to by either using a statement about being parallel or perpendicular, or if it wasn't parallel or perpendicular, you're just going to be given 2 points on a line. Once you find the slope, the rest of these question types become rinse and repeat. All you're going to do is you're going to take a point which is on the line, and you're going to plug in 3 for y, which is the same as g of x is the same as y, and 1 for x, and then you can solve for b. So that's what we'll do here. I'm going to get rid of some of these lines I've made. So I can now rewrite this as 3 equals 1/2 times 1 plus b, and now this is just going to be the same as 3 equals 1/2 plus b. So I can simply subtract over 1/2, and I will get that 2.5 equals b. And remember, this is our y-intercept, and that's what b is in our y equals mx plus b formula. So we now know that g of 0 equals 2.5, or you could bubble in 5 over 2 on the SAT. When you're bubbling in your answers, make sure you reduce them down all the way. Now this is going to give you 2 more lines practice questions where we're doing nearly the exact same series of steps. This is going to be where you have to solve for the slope first, and then plug back in to solve for the y-intercept. And here we're going to have to solve for the entire equation of the line, and then we can plug in 8 for x to figure out our answer there. Now, the last thing we're going to run through is special right triangles and one formula that pretty much no students I've ever worked with knows, which lets you solve for equilateral triangles in 15 seconds instead of having to split it up into 30, 60, 90 triangles. But the special right triangles are going to be given at the front of the SAT test. I'm going to pop on the screen what they show you at the front really quickly. But one of the biggest things for special right triangles is being aware that this is one of the SAT's favorite topics to use on their difficult geometry questions. So if you see a difficult geometry question on the test, it is almost always dealing with special right triangles or similar triangles. And in a way, equilateral triangles are special right triangles because if we split them down the middle, we can create 30, 60, 90 triangles. But even if you can just kick yourself in that direction of knowing you're looking for special right triangles, you can start to solve these questions way easier. So we're going to take a look at question 30 from test 10 here. Now in the quadrilateral above, ABCD, we're given that AD and BC are going to be parallel lines, and CD is 1/2 of AB. What is the measure of angle B? This looks nearly impossible to solve unless we're aware that the SAT loves to make difficult questions around special right triangles. And I'm going to kind of draw out that special right triangle, which we're going to be using here, and just knowing that we can be looking for these can make our life a lot easier. And I definitely do this a little bit slanted, but we'll work through this. So we'll say this is our 90, this is our 30, that should not be our 30, this is our 30, and this is our 60. And our proportions are going to be 2x, x, and x root 3. Now, what we have to recognize for this question is that our hypotenuse is going to be twice as long as the side opposite from 30 if we're dealing with a 30, 60, 90 triangle. So since CD is 1/2 of AB, that also means if we take a line here, let's say this is point E, that also means that BE would be 1/2 of AB. And that is the exact same of our ratio of x to 2x. And that lets me know that, well, this must be a 30, 60, 90 triangle then. So this is 30 and this is 60, and this is going to be 90 because it's going to create a right angle there. Therefore, the measure of angle B is going to be made up of 60 plus 90, which is going to give us our correct answer of 150. One other quick little pro tip is, unless they tell you that the figures are not drawn to scale, they are drawn to scale. So we're probably going to be leaning more towards 135 or 150, even if we're just visually guessing. Now, the formula that can make your life super easy on the test is if you're ever solving for the area of an equilateral triangle, this is the formula that's going to get you there. It's simply root 3 over 4 times side squared. So when we're dealing with a lot of these questions the SAT loves, it can save us a ton of time and make your life super, super easy. So a graphic designer is creating a logo for a company. The logo is shown in the figure above. The logo is in the shape of a trapezoid and consists of 3 congruent equilateral triangles. If the perimeter of the logo is 20 centimeters, what is the combined area of the shaded regions of the logo? Well, if the perimeter, and they're all equilateral triangles, is made up of 20, we have 5 pieces here. So that means that each of them is going to be equivalent to 20 divided by 5. And well, now what we can see is we have equilateral triangles with side lengths of 4. So now we can simply solve for one of them, and then we'll multiply by 2 to solve for both of them by simply doing root 3 over 4 times 4 squared. And this is going to be the same as root 3 over 4 times 16, which is simply going to be the same as 4 root 3. And now since we're doing 2 of them, we're going to simply multiply by 2, and we're going to get 8 root 3. And that's going to be it for the video here. So this is going to give you your special right triangles practice, and this is going to give you your answer key for all of those questions. If any of these you get stuck on and you can't figure out, drop a question in the comments below, and I may film a short video explaining it, or just explain it in those comments to you. Don't forget to like and subscribe. I hope this video has really helped you out on your SAT math. If you're looking for a little bit more SAT math help, I strongly recommend checking out the free trial of my Ultimate SAT course. No credit card needed. It's going to cover the quadratics chapter, which is going to cover a lot of stuff which are common sticking points with students. So especially if you're cramming for this next SAT, it can really help you improve a little bit more.